This is one of a series of revision lectures produced by the Further Mathematics Support Programme for A-Level Mathematics. In this lecture we're going to be looking at the Edexcel Decision Mathematics 1 specification, and the topic is matchings. The specification talks about the use of bipartite graphs for modelling matchings, the idea of complete matchings and maximal matchings. You may well be expected to define these things. So a bipartite graph means that we have got two sets of vertices. Let's call them x and y, and with edges joining vertices in x to those in y. So the lines, the edges, go from x to y. A complete matching is where every member of x has an associated member in y that is joined by an arc. So every member of x is joined to a member in y. There's one arc going from every node in x to an arc, and every node in y has an arc coming into it. That's not always possible, so a maximal matching is one where we've got the largest possible matching for a given situation. So those definitions are given in the specification. If you don't have a copy of that, I suggest you ask one of your teachers to give you a copy of the glossary, which includes the definitions for bipartite graph and matchings. So here's a fairly typical sort of situation that we might face then. We're given two sets, let's call them x and y, where we've got A, B, C and D in x and 1, 2, 3, 4 in y. And the bipartite graph shows the possible ways that each of A, B and C can be allocated to the tasks 1, 2 and 3. We start off with a feasible matching. It's really anything can be used as a starting point. However, the usual thing is that the question will tell you some feasible matching to start off with. So in this particular case, I'm going to start off with A matched to 1, B matched to 2, and C matched to 3. Now, of course, that leaves D not being able to do anything because D really wants to do either task 3 or 2, and 4 needs to be done by somebody else. The specification then says that you should be able to use the maximal matching algorithm to improve matchings by finding alternating paths. Now, an alternating path is a path which starts from matching M, and we try to find a path from an unmatched value in x, the first set, to an unmatched value in y, the second set. In this particular case, we're trying to find a path which starts at D and ends at 4. And the path has to go so that it has an unmatched element in x to an unmatched element in y, alternating with arcs which are not in M at the moment, so one which is not in the matching, with one which is in the matching. So let's try looking at this particular example to see if we can find an alternating path. Well, we can go from D to 3, which is using an unmatched arc, and then from 3 we've got to use the matched one, which is going back to C. From C we could go to 1 using an unmatched arc, and then we must use the matched one back to A, and then from A we go to 4 using our unmatched arc. So there we have an alternating path starting at D and finishing at 4. We then change the state of those arcs. So what we do is, well, instead of C doing job 3, D is going to do it. So that means that C can't do 3, but C is now going to do 1. That means that A can't, but A can now do task 4. I'll show that happening on this diagram in a different color, so that what's happening is that we go from D to 3. We're not going to use that one anymore. From C to 3, we are going to then use C to 1, not A to 1, but we're going to use A to 4. Now that process goes from using 2 matched arcs, and because we then change the state, we end up with 3 matched arcs. So we're bound to increase the matching by 1. If we can find an alternating path, the matching must increase by at least, well, by 1. Finally, we would be expected to write down the matching that we found. Okay, what I'm going to do now then is to look at a full A-level question and go through and to show you exactly what you need to do. Remember that in exams you can't use different colours, so that what you're needing to do is to draw lots of different diagrams. You can't actually do what I've done here in an exam question because it gets too confusing. So here we have an exam question. Then this time we've got 6 points, so 6 people, Alice, Brian, Christine, David, Elizabeth and Freddie, that can be allocated to 6 possible tasks, 1, 2, 3, 4, 5 and 6. And the bipartite graph shows the possible allocations that could be made. So we're told to use a particular initial matching, so A to 1, C to 3, David to 4, Elizabeth to 5, and we should show that in diagram 1. Having done that, we should use the maximum matching algorithm to find a complete matching and list clear the alternating paths that we use to give the final matching. Right, well, going back to the first part then, we've got to show the initial matching on diagram 1. So it says that Alice is joined to 1, Christine to 3, David to 4, and Elizabeth to 5. So it's quite a simple initial matching. The question doesn't actually specify which order we need to do things in, so it's up to us in this instance. However, sometimes you will be asked to start at a particular point with your alternating paths. So what we have to do is to start at one of the unmatched ones, let's say B, and see if we can find an alternating path to an unmatched one in the second set. So let's say 6. Now we need to do that via our main diagram, our possibilities, but remember what we have to do is to have an alternating path. So if we chose to go from C to 3, then looking at our matching at the moment, we would have to then come back to C. And of course that's great because we can then go from C to 6. So we have an alternating path which is B to 3 to C to to 6. Now there are lots and lots of different possibilities you can use for this question. However, this is one of the possible alternating paths, and that's the one I'm going to use, so that now when we change the state, that becomes B is allocated to 3 and C is allocated to 6. So in drawing the new matching, which I'm going to do on the left hand diagram at the bottom, I would start off with those new ones. B is now allocated to 3 and C is allocated to 6. The other ones won't have changed, so we're using our alternating path, having changed state, to put the first two in. The others will stay as they were in the first diagram, going from A to 1, then D to 4 and E to 5. Now looking at our new matching, we can see that F is not allocated to anything, and neither has 2 been allocated to somebody to do it. So we need to find an alternating path, this time starting at F and finishing at 2. Again, there are lots of possibilities, but remember that it's got to be an alternating path. I'm going to go firstly from F up to 3. 3 is at the moment allocated to B, so we must go to B, which then means we could come back to 4. 4 is currently allocated to D, then from D we could come to 5, and 5 is currently done by E, and finally we get to our destination that we want up to 2. So writing that down, it was F 3 B 4 D 5 E 2. We change the state of that, so we get F 3 B is now doing 4, D is doing 5, and E is doing 2. And it's those I will put onto the diagram first of all to make sure we get them correct. F is allocated to 3, B to 4, D should have a double line on that diagram there, so D is now 5, and E is 2. Leaving us with others that haven't changed. A is still doing 1, and C is doing 6. So there's our final matching, which we should state. The easiest way to state it is just by going through alphabetically. A equals 1, B equals 4, C equals 6, D equals 5, E equals 2, and F equals 3. Now looking at the mark allocation for that question, there was a single B mark for the first diagram 1 where you put in the initial matching. The first path was given a method mark as long as some attempt had been done to find an alternating path, and then an accuracy mark for finding a correct alternating path and changing the state. There was a second method and accuracy mark for doing the second alternating path, and finally an A mark for writing down the final matching, not just leaving it on the diagram. Now remember that there are many different ways of getting through to our final matching. It doesn't matter which alternating path you actually use in your solution. However, the final matching is going to change, so if you do it in a different way, you will not necessarily get the same answer as somebody else, but all possible answers are marked in the same sort of way. And here's a second question, just to illustrate the fact that a complete matching is not always possible. So here I have a situation where we've got 6 people again, A through, well actually A, Amelia, Charlie, Ellie, Gemma, Jimmy and Saskia this time. And they have tasks 1, 2, 3, 4, 5 and 6. We've been given an initial matching in figure 4, and we're asked to use the maximum matching algorithm to improve this matching. So I'm going to start at G and see if I can find a path through that ending at either 1 or 6. Let's see if we can find one going to 1. So again, remember that we have to alternate between ones which are not currently in the matching. So that's G to 3, but then we must come back to E. I think this is actually quite a straightforward one this time. It goes, there's only one choice, we've got to go to 2, then back to A, then to 4, and S. Then we have a choice really, we could go to 6 or to 1, so let's go up to 1. So that was G3, E2, A4, S1. And when we change the state, that becomes G equal to 3, E equal to 2, A equal to 4, and S equal to 1. So putting that onto our diagram, first of all, G equals 3, E equals 2, A equals 4, and S equals 1. Then of course we've got the one which is already allocated and hasn't changed, is J to 5. Now the second part of the question says, explain why a complete matching is not possible. So we could look through the diagram and see if we can get a matching from C to 6. It's one method we could use. But if we look at that, we can say, well actually let's look at the original diagram and see if we can argue from the point of view of what's possible here. Well, a quick look at the diagram shows what the problem is. Task 6 and task 1 can only be allocated to Saskia, and she can't possibly do both tasks. Alternatively, we could argue that Charlie and Jimmy, the only thing that they can do is task 5. And of course, they can't both be allocated to task 5. So either of those arguments would be sufficient to gain you the 2 marks. That question then went on and altered the possibilities to allow you to get a maximum matching, to get a complete matching, but the method would be exactly the same as the 2 examples we've already done. The marking for this question was done very similar to the last one. There was a method mark and an accuracy mark for finding an alternating path, and then a second A mark for stating the improved matching. So we should actually, not just as I've done on the diagram, we should also state that A equals 4, E equals 2, G equals 3, J equals 5, and S equals 1 is our improved matching. And finally, the 2 marks given for the clarity of the explanation. So either B1 or a second B1 mark given for some explanation involving the impossibility of allocating 2 tasks to 1 person or 2 persons to 1 task. Well, that's the end of this particular lecture. Other lectures for modules can be found on the website www.furthermaths.org.uk.